We have seen that in 1905, Einstein proposed his special theory of relativity, where he boldly suggested two postulates. First, that the laws of nature are the same for observers moving with constant speed with respect to one another. These are called inertial observers. For example, I am standing at a sidewalk and you pass by in a car moving at 60 miles an hour. The first postulate means that the way nature works should not depend on how people move. This first postulate was not invented by Einstein. Galileo had already thought of this. The second postulate is really the one that is revolutionary. It says that the speed of light is the same for all inertial observers. Why is this weird? Well, let's say you are in a car moving at constant velocity and your cousin is watching you move in that car from the sidewalk. Let's say your speed is 60 miles an hour. Now imagine that you throw a ball forward at 20 miles an hour. For you in the car, the ball will be moving at 20 miles an hour. But for your cousin at the sidewalk, the ball will be moving at 20 plus 60 miles an hour, that is 80 miles an hour. The two velocities add up. However, if instead you turned a flashlight on, both you and your cousin would see light traveling at the same speed of 300,000 kilometers per second. In other words, the speed of light is always the same. It's an absolute. Einstein didn't know why the speed of light is constant for everyone or why its value is 300,000 kilometers per second. But he knew that if this were true, his two postulates explain away many problems scientists were facing at the time, including the failed Michelson-Morley attempt to find the ether. In fact, according to the new theory, the ether was unnecessary. Light was pretty happy propagating in empty space. Einstein's new theory with the speed of light being constant for every inertial observer had amazing consequences. First, an object in motion shrinks in the direction of that motion, something called length contraction. Second, clocks in motion slow down, that is, they tick-tock slower. Third, the mass of an object in motion increases. The closer to the speed of light the object moves, the shorter it is, the slower time passes, and the more massive it is. These three effects are against everything common sense tells us, and, in particular, they go against Newtonian physics, where space and time are absolute. The length of an object or how time passes does not depend on how observers are moving with respect to the object. In Newton's world, which, by the way, is the world we perceive with our senses, space is a stage where things happen, and time flows always the same way, like a steady river. The reason we don't see relativistic effects in our lives is just because our speeds are so much slower than the speed of light. These effects are really strange, but do they actually happen? Oh, the answer is yes. Length contraction, time dilation, and mass increase are observed in many, many experiments. In fact, for your GPS to work properly, it needs to be corrected by the effects of the special theory of relativity. And this because GPS is based on 24 satellites in orbit around the Earth, and even if their speeds of roughly 20,000 miles per hour are much, much smaller than the speed of light, still the effects of length contraction and time dilation would compromise the precision of the GPS measurements. So the effects of relativity are not just real, but they are useful in the technologies that we use every day. The success of Einstein's special theory of relativity tells us once again that reality is stranger than fiction, and that scientists are constructing a narrative to describe what we can see of nature. This narrative is always changing as our vision of the world improves through our instruments and our observations. But we must always keep in mind that there is no final chapter in this book. The story of the world that we scientists tell is a story that is always open to revision, as long as the revision describes things better.